we're doing this project is really an active source seismic survey to make full crustal images of these features shown in red and blue. So those are the V-shaped ridges. Now, you'll see that all of the lead institutions, they're all from England. And the funding comes from the UK, Natural Environment Research Council. But instead of using a British ship, which would most likely have been the James Cook, we made a barter arrangement with the US so that we could use the Marcus G. Langseth for data acquisition. So I see that Ross Parnell-Turner's on the call, and he was the one who tipped me the nod that they were looking for people external to the US to do barter arrangements. So that was big help. So the draw of the Langseth is that she's got superior facilities compared with what I could have accessed in the UK, because she's an ex-industry vessel, whereas the British research ships are all general purpose. So we were particularly interested in the airgun array and the 15-kilometer streamer and the specialist technical support which comes with all of that. But it was a true, or it is a true transatlantic collaboration, because we also used ocean bottom seismometers from the UK pool based in the University of Durham, the one that's managed by Chris Pearce. So this project was quite a long time in the planning. I proposed it before COVID, and the funding was approved in 21, but then with the post-COVID cruise backlog, we had to wait for years before it eventually got scheduled. So the science in the project centers really around mantle processes. So we've got here a map of dynamic topography produced by Nicky White's group. So that's the component of Earth's surface topography that's supported by mantle convection. And the biggest red spot on this map is centered on Iceland. That's the head of the Icelandic mantle plume. So traditionally, Hawaii's been considered to be the most vigorous convection cell within Earth's mantle at present, but more recent thinking is that it might actually be Iceland that's the most vigorous. And the specific physical process that we're studying is called thermal plume pulsing. So as I run this simulation, you see the initiation of a plume structure, but when I run it again, in a minute, I want you to look carefully at the plume stem here, because you'll see that the flow in it is unsteady. The pulses detach from the base and move up the stem very fast, and then they spread outwards within the head. So watch closely the base. There. There again. Yeah. So hopefully you all saw that. So this hypothesis, the leading hypothesis to explain the V-shaped ridges, is that they are the world's best record of mantle plume thermal pulsing. So in this hypothesis, the pulses of hotter mantle periodically arrive beneath Iceland and spread radially outwards beneath the surrounding ocean. And we know that oceanic crustal thickness is proportional to the temperature of the mantle beneath the spreading axis. So as these temperature pulses propagate outwards from Iceland, they build V-shaped ridges where they interact with the spreading axes, both to the south and also to the north of Iceland. And importantly for getting funding, plume pulsing is also suggested to have affected climate, because it can potentially change the depth of the oceanic gateways either side of Iceland, and that can affect the Atlantic meridional overturning circulation. But there are alternative models to explain the V-shaped ridges. Possibly we might hear about some more of those next. So Dick Hay suggested that they were formed by propagating transform offsets. And then Dick and also Fernando Martinez proposed that patches of active damp upwelling propagate laterally beneath the dry solidus rather than thermal pulses. So to resolve these issues, our take on this is that to resolve them, we need both geophysical measurements and geochemical measurements in the same place. And the diagram shows where the geochemical data sets are. There's a high density of dredge sampling along the mid-ocean ridge itself. And the data over here, we can see chemical variations that correspond to V-shaped ridges. So the ridges are highlighted with these pink stripes. And the ridges are more depleted in trace elements than the troughs, and that's shown by the minima in these curves here, aligning with the pink stripes. So that, on the face of it, is evidence for a thermal control on melting. So we also have a series of IODP boreholes that were acquired off-axis. That's Expedition 395 that sailed in 2021 and then again in 2023. So at this stage, or prior to Impulse, we have a good geochemical data set, but the geophysical data set was poor in comparison. There were only 2 active source profiles of a few tens of kilometers long, both shot in the 90s with 8 to 10 receivers. So this one in the north was run by Bob White. This was the Ramesses experiment down in the south. That was a joint seismic and EM experiment that was run by Chris Pierce and Martin Sinner. And neither of those crosses a complete V-shaped ridge cycle. So that's really the opening for Impulse. Our first objective was to acquire the first full crustal seismic data set across multiple complete V-shaped ridge cycles. And we're using those now, beginning to use them to disentangle fluctuations in magma productivity that stem from mantle melting, from ones from what quote unquote tectonic noise, which we're expecting to be there when coming from crustal accretion processes. And then we're going to carry out joint geochemical and geophysical modeling and think about the relationship between mantle processes and environmental change later in the project. So the acquisition centers around 2 long profiles, and those are marked by these yellow boxes here. So the box labeled PA, that's a profile along the axis of the Reykjanes Ridge. And the box PF is a profile that's parallel to a plate spreading flow line. So you'll notice that the spreading direction is oblique to the mid-ocean ridge in this part of the world. So we shot both of these profiles twice, once for ocean bottom seismometer data with a 60-second shot interval, and then again with a 50-meter shot interval with the 15-kilometer hydrophone streamer. And the source was a 36 airgun array, total volume over 6,500 cubic inches. And as I mentioned, this is a huge advantage of the Langseth. You know, it's an ex-industry vessel, and she's designed and fitted out to operate this source. And the technical crew were ex-industry people and really excellent. The whole thing went very smoothly. But we were operating under US environmental regulations, which are considerably stricter than EU and UK regulations. So we needed 8 professional protected species observers. So I think that was a slight point of friction in the barter negotiations between NERC and NSF, but we got there in the end. So a bit more detail on the ocean bottom seismometers. We had 50 instruments and a 4-person technical crew from the UK facility at Durham. So we made 140 deployments and recovered all but 1 of those instruments. We saw where the other went, but we couldn't get to it because of weather and equipment issues. So it was a moral victory. We did 1,120 line kilometers of shooting into those instruments, and then 136 of them returned usable data. There were 3 logger or sensor failures, and all of those were on the first deployment transect, actually, and we identified and fixed those before the next 2 deployments, which helped with the success. So we acquired the entire OBS data set almost exactly as planned. So I would very strongly recommend the Durham group to work with. Certainly the US operators there, who are based at Lamont, they were also super impressed with the guys from the UK. So the flow line profile here in topography and gravity there, it's designed to cross 4 complete V-shaped ridge trough cycles, and that's covering, importantly, both conjugate sides of the mid-ocean ridge, which is what we hope will allow us to disentangle mantle melting and crustal accretion processes. So the spacing, the OBS spacing was 4.4 kilometers along this line, and it coincides with the IODP Expedition 395. You can see those in light blue there. And the axial profile is designed to cross two complete V-shaped ridge trough cycles. We had 11-kilometer OBS spacing over a total distance of about 600 kilometers there. So I think that's probably one of the longest OBS lines that's been done. And we aim to show here how the V-shaped ridge melting anomalies are superimposed on the regional hotspot-centered anomaly. And this profile is coincident with a whole lot of the dredge samples shown in the small light blue circles there. So I'll very quickly flash up some of the data. Fortunately, I can see that Nermit is on the call, so he can talk about this at more detail if we get questioned. This is an OBS gather reduced to 8 kilometers a second, showing P wave arrivals out to beyond 70 kilometers. We see some S waves as well. This is reduced at 4.5 kilometers a second. And this is just an example of the streamer data. So as well as the obvious reflections, note here, we can see refractions, which are clearly visible at offsets out to 15 kilometers. So the progress to date, obviously we achieved objective 1 in summer 2024. And since then, we've been working on the second objective. And this work is being done in Southampton by Nermit Dabaria, pictured. He's working with alongside Tim Henstock. And we've got a very large data set, as you will have gathered. So Nermit spent the entire year last year preparing and then modeling the OBS data, just focusing on the flowline profile. So that's maybe just a quarter of the total data set. And right now, we are working on the interpretation of his velocity model in terms of the second objective. So that's disentangling mantle melting and tectonic crustal accretion processes. So what I'm going to say going forward, these are initial thoughts in advance of our first conference presentation at EGU. We've got 2 there, I think one in my name and one in Nermit's name. So this is Nermit's model. I'm not going to go into the technical details, except to say that it was built from modeling a lot of crustal refractions, mantle refractions, and MOHO wide-angle reflections. All those pics have been inverted by him using the Tomo 2D software package. So straight away, we can see considerable topography on the MOHO. So the MOHO reflection is actually easier to see on the lower panel. The lower panel is the velocity residual with respect to the starting model for the inversion. So the crustal thickness varies along the line between 6 and 9 kilometers. Oops. So you could also see distinct lower crustal velocity variations. So we were excited to see those. They are very robust features. They came out very early in the modeling process. And you can see straight away that they're roughly symmetrical about the spreading axis. So let's have a look at how the seismic velocity structure correlates with the surface expression of the V-shaped ridges. So that's shown by the seafed topography here from one of Ross's papers, and then the free air gravity field at the top. So arguably the clearest features on here, the topographic features after the axis, are these scarps. So there's one here and there's another one here. And they bound these V-shaped troughs in the gravity field. So that's trough 1, and then outboard of that is trough 2. So those boundaries of the surface features match well with the boundaries of the lower crustal seismic velocity field. So we're thinking that these represent these lower crustal velocity anomalies. They are indicating distinct differences in the composition of the lower crustal cumulates. And they're symmetrical about the ridge axis, and they correspond to the most pronounced V-shaped surface features. So it does look potentially like a signature of a pulsed magma supply. So just now let's look at the symmetry in more detail, because symmetrical features imply a magma supply control, whereas asymmetric features would indicate more the influence of tectonic processes. So focus here on younger crust up to 5 million years old. That's the first V-shaped ridge cycle. And I'm showing 3 different measures of crustal thickness here. The red curve is from Nimit's seismic velocity model, and that's plotted as moho depth. So thicker crust is downwards, yeah. And the blue curve is a proxy for crustal thickness from residual depth from one of Ross's papers. So that's the backstrip depth to the top of oceanic basement compared to the depth predicted by a plate model. And the heat map, that shows the free air gravity field, which is also a proxy for the relative variation in crustal thickness. So the point here is that these curves match well in the sense of their motion. In particular, the blue curve, that's the crustal thickness proxy based on topography, it matches the seismic red curve very well, down to million-year scale detail. So there is clearly a lot of symmetry about the spreading axis here. There is also some more minor asymmetry, but that does suggest to us that we're seeing a cycle of melt productivity here that has built the youngest V-shaped ridge trough cycle. But the story is more complicated when you go to the older crust. So just short of time here, so I've just highlighted this box 5 to 11 million years old crust. And here you can see that the red curve, so that's the seismically measured crustal thickness, it's less symmetrical about the spreading axis here. The crust does thin away from the axis on both sides, but the gradient is steeper on the eastern side there than the western side there. So it does look like potentially tectonic processes are operating here. And intriguingly, more intriguingly, the crustal thickness measured on the seismic velocity model is quite different in this grey box to the crustal thickness proxies. So we were expecting in this region relatively thick crust, as shown by the blue line, but actually the crust turns out to be, in fact, much thinner. So this is what we're trying to figure out now, and hopefully we'll have a better handle on that by EGU. So one issue could be that those lower crustal velocity anomalies that we saw, they're probably also density anomalies. But the crustal thickness proxies, of course, we're all assuming a constant density. So we're thinking about whether accounting for those variations along the line could maybe account for discrepancy between these different crustal thickness indicators there. And another thing that we need to work on is the age model. So this figure is plotted relative to the global age model, this one from Dietmar Müller's group. So to measure asymmetry properly, we're going to need a local age model that's determined directly from the magnetic stripe data on both sides of the ridge axis that we collected on the ship. So to finish, when we've obtained the first full crustal seismic data set across multiple VSR cycles, and I've shown you hot off the press Nermit's velocity model for our flow line profile. Importantly, it shows both sides of the spreading axis. So I've put his address at the bottom here, in case anyone would like to take up with him any technical details. So, but at this stage, we think that we see evidence for fluctuations in magma productivity and magma composition. So that would be evidence for pulsed mantle melting. But I've not gone so far here as to attribute that to thermal pulsing, because I haven't gone through in this presentation the geochemical signatures that match those geophysical signatures. We need to think about those before attributing to thermal signatures. And there's quite a lot of work still to do. We've got the axial profile to do, and then we also need to incorporate the streamer data to give us higher resolution in the upper crust. So that's it.